Hi everyone, thanks for coming. I know I have this is a tricky slot for a session after lunchtime, so it's a great responsibility. I need a great power for this, so I will do my best. Thanks for the introduction. Just a couple of other words about me. So you're asking who the hell is this guy? So my name is Guglielm, and I'm based in Dublin, Ireland. I joined MSD mid-February this year. For people coming from North America, probably you know the company as Merck is one of the top biotech pharmaceutical companies in the world. And previously I was in another healthcare company called Optum, which is part of the United Health Group, IBM, and FAO, which is an agency of the United Nations, just to have a quick summary of what I've been in the 11 years before joining MSD. My field of expertise is in deep learning, machine learning, but also coming from extensive experience on software engineering. And for some reason, I always end up on solving problems and putting things in production, also in the data science space. Now it's a little bit different in MSD, the challenges, but anyway, in the manufacturing. So trying to work on this space. I published my first technical book in January. The topics I'm going to cover today are also in the book. There is just an update because, of course, things change, framework change. And I love cooking, so in particular, I'm good on preparing the real Italian pizza because I'm Italian. So in the Q&A session of the rest of the conference, if you have a question on how to prepare pizza, so I'm available. You're welcome, not just for tech stuff. So some numbers about the company, so I don't want to spend much time here because you'll be more interested in the main topic. Just to say that MSD is in Ireland since more than 50 years, and some of the top products of the company are produced there. And so there are challenges in the trying to make the manufacturing process more data-driven and more digital. So that's where I'm involved now in the company. As mentioned, I'm in Dublin. I use these events to give a quick word about the Dublin Tech Hub, because in some countries in Europe, like Italy, the country I came from, some illuminated politicians always refer to Ireland such a fiscal heaven, place like Cayman Islands, which is not, because of course there are facilitation in terms of taxes for companies. If you're a startup, medium-sized company, a big company, there are facilities, but this means that you have to create jobs and create innovation. The more you create there, the more you are rewarded. So it's not just a fiscal heaven. There is a really hub that is attracting lots of talent from all Europe. So just I want to notice this. So how many people are working on deep learning projects? Okay, there are a few of them. So I put just a couple of slides just in case to summarize what deep learning is. So it's a subset of machine learning which uses neural networks or better multi-layer neural networks. It means that for each network you always have an input layer, an output layer, and a given number or given combination of inner layer that are called hidden. And this combination defines the class of problems that you could solve with this particular model. There are different implementations of a neural network. Each one specializes in a specific class of nonlinear problems. For example, you have CNNs to solve problems on object detection or object tracking, LSTMs for time series forecasting, for example, RNN for text generation, and so on. There are many of them and different implementation. And but the process is the same as for machine learning. So you have your model, you have a training data set and testing data set. You train your model. It's an iterative process. So when you reach the desired accuracy, you put the model in production. There are new data coming, and the model starts to do prediction. And of course, this is always a never-ending process because you can discover new patterns, other things, and so you have to train again the model with new data, or if putting things to production, you observe that there are some false positive or false negative, so you have to go back to improve the accuracy of the model. There are different applications of deep learning. In particular, at the moment, I'm involved in the manufacturing, but there are others also in other spaces, such as natural language understanding. In the last couple of years, I saw also different new cases in quantitative finance and many, many others. So this is not a comprehensive slide. And sometimes you have to train your model in a distributed fashion on Apache Spark because for different reasons. For example, your model is, your network is complex. You have big volumes of data. Imagine, for example, a company which is processing 1 trillion claims per year, or some other use cases in manufacturing when you have different machines on the same chain, sending data, generating data. Or if this morning attended the talk by Luca Canali, there was another use case at CERN in Geneva on the data they're receiving from their experiments. So in that case, even if you have GPUs, you can rely on a single machine with multiple GPUs. So you need to do this on top of Apache Spark. But there are some challenges on this. This doesn't come from free because there are several frameworks available for deep learning in Python, in Java, Scala. But the execution model is different from the execution model of Spark. You know, in Spark, you have tasks that run in parallel. If one of these tasks goes down, it's up to Spark to try to restore it. And this doesn't affect the work of the other tasks. This couldn't happen when you train a model in deep learning, because if a task goes down, you have to start the training from scratch. And the training could, depending on the size of your data set, and could last for hours, for days. So imagine this is a big impact on productivity and also on the service that you want to deliver to your customers, or in some cases like mine, to the patients for the company. Another challenge is the GPU management, also scarcity of GPU could be another reason to move to Spark. And because the configuration and the management could be a nightmare, because some framework don't provide facilities to do this when you do training on distributed fashion. And then last but not least, you have to pick up one between performance and accuracy, because in order to achieve the best of performances on training your model, if you run things only on the JVM, you have to sacrifice something in terms of accuracy, because Spark and the JVM better needs to do some rounding on some values, so the result you achieve are not the best. Or vice versa, if you want to achieve the best accuracy, you have to sacrifice performance, so it means that your training will last longer and probably wouldn't be acceptable in some cases. In order to solve these problems, when we started this almost 3 years ago, we evaluated 3 different frameworks for the JVM to do distributed deep learning, and the final choice was about on DL4J. I'm not covering the details why we discarded the other 2 for our cases. I'm not going to be prescriptive. In our case, this was the best choice. Probably is the best choice in different use cases. But anyway, feel free to ask me a question after the talk on comparing this with other frameworks. The reason for choosing a framework that runs on the JVM are mostly because the first use cases we had were in basically DevOps problems. And so the people working on those teams were very skilled Scala and Java engineers, very good on doing things on Spark, but with no clue at all about data science. So this framework is a distributed framework for JVM languages, so not just Java. I know there is the J in the name, but also for Scala, Kotlin, or whatever runs on the JVM. There is also a version for Android. And so the entry point for them was really good, because they know how to implement Spark application, how Spark internally works, and through this high-level API, start to learn things about data science, in particular about deep learning, the internal of neural network, the concepts, how to train, evaluate this network, how to do hyperparameter optimization and things like this. And natively, since the first release, is integrated with Apache Spark and Hadoop. This doesn't mean that you have to use this framework only if you use Hadoop and Spark. So you could have also a different cluster manager for Spark. We use this on Kubernetes, and also your data could be elsewhere. In our cases, most of the data were on Amazon S3, but also other data storage, and no impact at all on performances. And you anyway write the same code wherever your data set are. And Of course, this framework, since the start, works the same code you implement in deep learning 4J, work on CPU, GPUs, or in a mixed environment. So you have just to add the proper dependency on your project descriptor, depending on which hardware you're running. And there are some optional configuration params that you need to set up in your Spark application configuration. So you don't touch the code. It's the same if your underlying hardware changes. So the framework is modular. There are different modules that you need just to import those that you really want to use. So you don't need to import the full framework. This is not a comprehensive list. So there are many others. I want just to give some words about the DataVec module, which this is one of the most important modules of deep learning 4J because it allows to transform your input data, whatever the format is, into tensors. The input data could be images, audio files, video files, documents, whatever, and they are transformed automatically into the features to train your models or validate your models. NN is the core module for this framework, so you definitely need to use it. Deep Learning 4J Spark is the module if you do training on a Spark cluster. Model import is a model that allows you to import pre-trained Python models into Deep Learning 4J, and then you can start doing inference with those models. You can retrain them, and you can also modify the structure of the network, but using Scala or Java code, depending on your Spark application. I will keep the last one, ND4J, in a minute, because this is pretty important to understand. This is an example of code of deep learning 4J in Java. This is the way you create the configuration of your neural network. In this case is CNN. As you can see, you can set up the updater, the weight initialization strategy, all of the layers there. And as you can see, it's a very high-level language. So even if probably you don't know Java, from the class's name, you can understand what you're doing here. If you so imagine a software engineer starting with data science now with this kind of API becomes really upskilled on this and more curious on learning more. So initially they don't need to know the linear algebra or the maths behind this, but it works. If you're good in Java Scala, you can do this. And once you create your network object, passing this configuration, you can start training and evaluating the model. There is a specific fit method for this and using the dataset that you already transformed as part of DataVec. So this is some sort of end-to-end framework at the end. It's not just for training neural networks, but from the data ingestion, transformation, training, and putting into production, all of the elements of there. There are other components also for deep reinforcement learning. The models that you implement this way could be used for a GAN. So there are different things that you could do with this powerful framework, and everything in Scala or Java. ND4J was born as a component of Deep Learning 4J, but now it's some sort of project per se. So basically, it's a library that its core is implemented in C++ or CUDA, depending if you want to run this on CPUs or GPUs. But this is transparent to you as Java or Scala developers, because it exposes high-level APIs in Java or Scala. The goal of this project was to fill the gap between Python and the JVM programming languages in terms of tools for linear algebra, matrix manipulation, things like this. This has been inspired by NumPy. If there is some Python developer here, probably you know what we are talking about, and show you just a little bit of code. You do things in Java in this case, but also in Scala, and you forget about the low-level implementation. And this component is used anytime by Deep Learning 4J to do things, to do different things. So this is important, and we see in a few seconds why. What's the key role of ND4J on training, implementing and training networks with Deep Learning 4J. So I didn't put any slide about Apache Spark. I'm assuming if you're attending a Spark summit, you know what Spark is, just in case there are the Databricks guy over there. You can ask them. And so these three technologies, Apache Spark, Deep Learning 4J, and ND4J, bring something that make this a powerful combination. Deep Learning 4J, as I've shown before, provides a high-level API to design, train, configure, and evaluate multi-layer neural networks, but this is enough because if you use Spark in some situation, you also take advantage of the Spark features. You know, it's really good in performances for several problems, whatever you do, if it's something that you're doing in streaming fashion or in a batch fashion. But there would be a problem in terms of performance if you try to do this specifically for training multi-layer neural network, because if you do something on the JVM, then you have to pick up one between the performance of accuracy. But because Deep Learning 4J uses ND4J behind the scenes, which is a library that runs very close to your hardware, to your CPUs and GPUs, that becomes a powerful combination because you overcome all of the problems that you will have if you try to do distributed deep learning with some other frameworks. And this worked very well for our use cases since day one, but we discarded some other framework for this. A couple of words about how the training could happen with Deep Learning 4J. There are two strategies. It's up to you, data parallelization or model parallelization. Data parallelization is the easiest to configure because basically it means that you train the same model, but using different portion of the data set on different nodes of the Spark cluster. So if you are very skilled on using Spark, so this is really easy to do. While the model parallelization is really tricky also for data scientists because it means that you have to train one or more layers of the same network on a single node and using for each node the same data. And if you don't know the exact relationship between your layers, you could screw up things. You will have results that are totally meaningless. So I would suggest you to start with data parallelization. Anyway, it's a good strategy. It's not because it's easy. Couple of words about how the training happens in Spark with Deep Learning 4J. There is an abstract class called Training Master, which has at the moment just two implementation. Up to Deep Learning 4J 1.0.0 alpha, the only implementation available was the parameter averaging. Starting from the next version, there is an alternative, which is the asynchronous stochastic descent gradient. Which in the future will become the standard. Probably the parameter averaging will be deprecated, but at the moment you can pick up one of them. I'm not going to dig into pro and cons of these two, but anyway, whatever choose you do for your implementation, you win because they are quite stable and take advantage of your Spark cluster anyway. So you don't need to care about the details when you start with this framework. So far the good news, but it seems a powerful combination, but something could go wrong. There are different things that could go wrong. Today I'm focusing only on memory management. These things that I'm going to share today and others that I cover in the book weren't covered by the official documentation in the earlier version. So we learned this from experience. Now most part of them are in the documentation, but the error that these things generate are really tricky to debug. So I'm going to share what I have to do. I want to mention just that if you are a Spark developer or a Java Scala developer in general, all the things that you know in terms of best practice in development on doing things with Spark still apply. This don't change. So another good thing of this framework is that it adds something more to the stack, but you don't have to change what typically do with Spark and Scala and Java. Same as if you're a data scientist, the best practices you do in order to pick up the right model for a specific nonlinear problem or the way you design a model, that's still valid. There is something more just to understand to take the most from this tech stack. So if you look at this snapshot, this has been taken in a local Spark cluster of 3 nodes using CPUs, not GPUs. The chart on the top shows the 2 lines. The red one is pretty constant in time and represent the usage of JVM memory utilization while this model is under training. while the blue curve that is going up and down with reaching some peaks represents the utilization of non-heap memory. Why this? Because, as I mentioned before, ND4J, the core of ND4J has been implemented in C++ or CUDA, so you have to expect a lot of objects into the off-heap memory, which is something that in most cases in a Java Scala application you don't have to care too much, but this is the key to understand how to very well manage memory when training these things. And this chart has been taken in a situation where the training was going well. The memory workspaces weren't configured very well because I did this on purpose to show this difference. But anyway, this is a normal situation in deep learning 4J. And these are the two strategies, the two approaches you could follow to manage memory in deep learning 4J. The first one is the JVM garbage collector and the weak reference tracking, nothing new here. And the second one is specific implementation for deep learning 4J, which is the so-called memory workspaces. The idea behind both this implementation is the same. So once you finish using, your application finished to use a multidimensional array, the off-heap memory associated with it should be deallocated so that could be used by somewhere else. What is different is that in the case of the JVM garbage collector, as soon as this multidimensional array is not needed anymore, its memory is deallocated with no assumption that this could be probably reused by something else. While in the memory workspaces, when this happens, there is no deallocation or reallocation, so it means that this could be faster, and that's the right strategy, in particular for deep learning training, because if you think of the training as an iterative process, imagine you have a lot of calls of the garbage collector during this, your performances will be very, very bad. So the second one is the strategy that I suggest if you do things on deep learning 4J. Unfortunately, it's not the default, so you have to configure the memory workspace yourself, the configuration, but and this is something that people don't check sometimes in the documentation, in the chat, official chat for this project. You see a lot of people struggling, or they don't know how to cope with the garbage collector calls, even if now this has been added to the documentation. One thing that people typically don't do, even if they know how to manage the memory workspaces, is to, if possible, disable the periodic garbage collector calls. There is a specific method available from the memory manager in ND4J, and this is not just the ideal situation, but also in some production cases could be the reality, because in several models that my teams implemented, the amount of object into the heap space was really small. There were much more object in the off-heap, so you can really turn off the periodic garbage collector calls. Or if this is not your case, there is an alternative in ND4J using the same memory manager but a different method, so you can reduce, you choose the interval, the periodic calls to the garbage collector. This is important because if you don't do this, even if you set up correctly the memory workspaces, you're still staying on the garbage collector strategy. So you added some code that basically is doing nothing, which is the situation that I showed before in that snapshot. So this is important. People ignore this configuration and they think that they're doing memory workspaces, but it's not the case. Before someone asking, in other talk, people ask me where the previous snapshot has been taken. Deep Learning 4J provides some visual facilities. This one is when you train a model, is a web UI. This is just a landing page. There are different pages with different charts where you can check how your training is going on, and you can spot potential problems. This is very powerful for data scientists, because from this chart they could understand where something is going not as expected in the training, and you can stop this before the training finishes, fix the configuration, the Apache Spark configuration of the model or whatever is going bad, and restart the training, and this saves you a lot of time and of course money. And there is also one of the pages, a graphical representation of the model and the training. Clicking on the single layer layers, you have dozens of charts to understand how things are going on for each single layer, so you can do a fine-grained check of your models. This is not the only visual facility available in deep learning 4J. There is a problem when you do this on Spark. There is a dependency conflict between the deep learning 4J UI library, which is the one that provides the server to start that UI, and some Spark dependencies. This hasn't been solved yet in the latest implementation, but you can do in two different ways. The first one is that the same module provide you API to collect data, stats of the training, and save them on a file system or something that is based on HDFS, and then start the UI offline and visualize them offline. But in this case, you lose the advantage of having information in real time. So the best alternative is to execute the UI in a different JVM process, not in one of those running some Spark nodes or the Spark driver. And the same API can allow you to upload these metrics from the drivers to the UI, and so you still have the information at real time, which is the best case you have. The payload of doing this is negligible, so you don't see, this doesn't affect the performance of your training on Apache Spark, so it's the best solution in this case. Coming back to the other problems on memory management. So data serialization, you know, it's really important in Apache Spark, in any Apache Spark application. You know, there are two ways of doing serialization in Spark. One is traditional Java, which is the default if you don't specify anything. The other one is the Kryo framework. Pro and cons of these two approaches. Basically, the Java serialization works very well with anything implements the serializable interface, but the problem is that the serialized object has pretty big. So imagine you have to persist them or move them across the network. This could have a significant impact on your performance of your model. While in Kryo, the objects are really small. The problem is that not all of the implementation supports Kryo. So sometimes you have to pick up one, or anyway you can create a list of objects that support Kryo, and for all the others do serialization with the Java. So if in your case Kryo is supported by your implementation, that will be the best choice. So probably you choose Kryo, and be prepared to have a lot of null pointer exceptions ready to really hard to debug. The reason is that, coming back to the memory organization in deep learning 4J, Kryo has been implemented to work with the Off-heap data structure, which is you have plenty when you train things with deep learning 4J. But there is a solution for this, which is not covered in the documentation, but of ND4J, but is available. There is a specific module that you have to add to your project dependencies, ND4J Kryo, which basically asks you to use the ND4J Kryo registrator, and you have to set up this in your Spark application configuration as follows. This means that Kryo, through these modules, could work the same way on serializing objects that have a portion or most part of their sites into the off-heap memory. And this is a simple way, but if this is not covered in the documentation, this is really hard to understand. Another issue with the off-heap memory, so still they're causing problems. So you know that Spark, if you have object with a big off-heap components, it has some problems on trying to persist in them, which is the case of deep learning 4J, because anytime, whatever is your model implementation, you use multidimensional arrays and dataset. In this case, dataset is not the dataset from the Spark API, is the ND4J dataset data structure. The problem is that Sparks drops part of the RDD object on the estimated size of those blocks, but it doesn't take into account the content which is in the off-heap memory. So the estimate is totally wrong, in particular in those cases where you use memory only or memory and disk persistence levels. So this is this causes again, a lot of out-of-memory exception, and before you bang your head in trying to understand them. So the strategy is this one. So in case you're using the memory-only persistence level, you have to switch to memory-only SER, or if you're using memory in disk, switch to memory in disk SER, because this way, and you have to do this just for the RDD of dataset of a multidimensional array. This means that when you do use this persistent level and do serialization, the serialized objects are fully stored in the JVM heap memory. So Spark knows how to distribute these blocks, and there is no off-heap memory for them. So Spark works as usual. So this is another problem which is really hard to figure out. Deep Learning 4J, in order to set up the memory limits, work with the usual JVM command lines arguments that you already know, XMS, XMX. And there are two extra configuration params, max bytes and max physical bytes. In particular, max bytes is the most important one to specify the size of your off-heap memory limit. One suggestion I give you in terms of setting up the memory limits is that don't use high value of XMS with the XMS option, because at the end you wouldn't have enough of heap memory for your application to work well. So you will have run again in out-of-memory errors. A quick example, imagine you're running Spark on commodity hardwares and a system with 32 gigabytes of RAM. Imagine you set up, I've seen people doing this, XMS to 28 gigabytes, and then you have just 4 gigabytes for the off-heap memory for the same Spark application, the operating system, and whatever is running on that machine, and then this will screw up at the first iteration, at the first epoch of the training of your model. So this, don't do this, please. And in general, best practice is that you can check these things also with some tools like the Cubul Spark Lens. The size of a given object that uses ND4J objects such as datasets of a multidimensional array, it's very small into the heap memory, but it's bigger in the off-heap memory. So try to set up more space in your nodes to allow to store more objects in the off-heap memory. So this is a typical situation in Deep Learning 4J. So that's why turning off the garbage collector periodic calls couldn't be a problem for you, or just minimizing them. A couple of words for people that use Python. You do deep learning in Python. There is a module called model import in Deep Learning 4J, which allows you in the initial version just to import a Keras model with any flavor of backend, including TensorFlow. But in the latest version, you can also import a pre-trained model implemented in TensorFlow. It supports also TensorFlow 2.0. When you do the import on your production stack, which is mostly based on things implemented and running on the JVM, such as Apache Spark, Kafka, the streams data collector, Solar, Elasticsearch, Hadoop, whatever. It means that all of the consideration about memory management happen in the JVM, so they apply there. So we are no more in the Python environment, but we are in the JVM world, and you set up things the same way you do for Spark applications for training deep learning models in Java, Scala, Kotlin, or any other JVM programming languages. I did last week a talk at the Moscow at the Big Data Days about these particular things. It requires another hour to understand how it works, and I understood that it's a pretty hot topic. So if you're in Madrid next month, I'm going to do a follow-up of that topic. So if you're implementing things in Python, or you have a data science teams that are more familiar with Python frameworks, then you can put this into production, into Deep Learning 4J, taking all of the advantage of that infrastructure, and rather than run banging your head on configuring GPUs or understanding how to set up these things for deep learning on Apache Spark from the Python side, which is not yet mature on that case. And before moving to the Q&A session, forgot to mention that deep learning for J is not meant to work necessarily with Spark, of course. If you have a Spark cluster, you use it, and there are cases where you can't do things without Spark. But there is a specific class called a parallel wrapper, which allows you to do the training in parallel, for example, in a single server where you have multiple GPUs. In that case, probably it's the case that you don't need Apache Spark, but anyway, you could use deep learning for J, and of course, all of the consideration about memory management still apply, and all the other benefits of using deep learning for J. That was my last thing, just to all the things are collected in my book, which is going pretty well on torrent as well. If you look at the charts, it's on top of the book about Spark. So that's good. So people are interested in. So the goal was to share these things, and 3 years of starting this, doing this thing, the training of models in a big environment. And we have now the Q&A session, and feel free anyway to get in touch on LinkedIn, Twitter, of my blog, or of course I'm around today and tomorrow, so the networking is the best part of conferences. So we could start the Q&A session. Thank you.
Great, thank you. That was reminds me a lot of the days spent troubleshooting NPEs and OOMs. That's never a fun thing. So I think those are some great debugging tips and tricks, excuse me. I need some coffee too. But is there anyone with a question? I'm happy to hand the mic over.
Yeah, there's one.
Hello, how are you doing?
Good, thanks.
You just mentioned that you had this, or maybe you're still running it on Kubernetes, right?
Yeah.
Okay, did you have any words to share about that? Because I have a complete Spark cluster running on Mesos, or Mesos.
Yeah.
Okay. I call it Mesos, by the way. So I don't know how well will that go using DL4J.
Oh, it's a long story to understand our Kubernetes cluster. So basically, we start to do these things with deep learning in early 2017, where Spark was still in release 2.2 something. So there was no support for Kubernetes, but our private cloud was based on Kubernetes. So what the team did was to import an open source project called O5 from Red Analytics. Basically, some way that allows you to span dynamically clusters, Spark cluster on Kubernetes, and you can scale up and scale down on demand. But that wasn't enough for us, because for some use cases it wasn't good, not just for deep learning. And the guys have to fork the project and did an internal implementation, which unfortunately is not open source, is proprietary code of the company. So that way we solved different challenges on spanning a cluster on Kubernetes using this O5 project. And by the way, with if you ask about specific problems on challenges with deep learning for J, we didn't face any on that event. The challenges were mostly on putting Spark on Kubernetes. Of course, if you run in a platform like Databricks or something else, don't have to care about the cluster itself. But anyway, deep learning for J is something that you could put in containers, and so that's not a problem. It's much more the deployment if you have to manage this of Spark on certain environments.
Any other questions? Thank you.
Thank you.
Hi.
You mentioned that you've compared to other algorithms. You didn't want to go into the details, but I'm just very curious. What are those other algorithms?
Yeah, the other two were frameworks. Were Big DL from Intel, another one from ThoughtWorks, which is called deep learning for Scala or something. I don't remember the exact name. We discarded them after the proof of concept because the Big DL is good if you have Intel-based hardware. If you move to some other hardware, your performance will screw up. So this morning there was a presentation of a use case where they have a partnership with Intel. So that's probably is a good choice, but not in our case, with was a different hardware. The other one was discarded because in early 2017 was not yet mature, but we noticed that was going to grow up as a framework. The challenge was that while in deep learning 4J you have very high-level API, if you're a software engineer and jump into this API, you will upskill also in the data science part because this has has been implemented by software engineers for software engineers, while the Spark for the deep learning for Scala had some API which could be comparable with the TensorFlow API. So they suppose that you're a data scientist and you know what is going on in how to implement a network, what's the algebra and the math behind this. So that was a big obstacle for us because the first use case where you use this were to solve some problems in our DevOps space. So we didn't have any support by data scientists. There was just me and the rest of the team, mostly software engineers. Then moving on, we had support from the data scientist team in the organization, and it was better. But to start and show evidence that this was working, we have to discard deep learning for Scala.
Great, thanks everyone. We're out of time now. By all means, as Guglielmo mentioned, find them for pizza recipes or otherwise around the conference. Please remember to fill out the surveys again, and thanks for your time.
Thank you, guys.